Welcome to a new video of a historical journey. Today, we present to you the Scientific Odyssey, discovery of elements and creation of the periodic table. In the fascinating world of chemistry, the history of the discovery of elements and the creation of the periodic table unfolds as a scientific epic that has evolved over centuries. This journey, filled with intrigue, discoveries, and collaborations, has shaped our modern understanding of matter and atomic structure. From the early alchemists to contemporary laboratories, each chapter in this narrative reflects the tireless pursuit of knowledge about the elements that compose our universe. In the dawn of chemistry, medieval alchemists embarked on the quest for the Philosopher's Stone, a mysterious artifact supposedly capable of transmuting common metals into gold. While their goals were more mystical than scientific, these investigations laid the groundwork for alchemy, which later transformed into modern chemistry. Over time, scientists began isolating and characterizing different substances, discovering individual elements. Since the early days of chemistry, various scientists have contributed to the discovery and conceptualization of individual elements. In 1766, Henry Cavendish identified and named the gas we now know as hydrogen, calling it inflammable air. A few years later, in the 1770s, Joseph Priestley and Carl Wilhelm Scheele independently discovered oxygen, labeling it dephlogisticated air. Simultaneously, Daniel Rutherford isolated nitrogen in 1772, naming it mephitic air. In the 18th century, Antoine Lavoisier made significant contributions to understanding the properties of carbon. In the early 19th century, Humphrey Davy isolated the alkaline earth metals, calcium, strontium, and barium. Additionally, in 1810, Davy identified chlorine as an element. In 1807, he also isolated the alkali metals sodium and potassium. Bernard Courtois discovered iodine in 1811 by treating seaweed with sulfuric acid, while Henri Moissan, in 1886, isolated fluorine through the electrolysis of hydrogen fluoride. Finally, in 1789, Martin Heinrich Klaproth identified and isolated uranium. These discoveries and contributions laid the foundations for modern chemistry and the subsequent creation of the periodic table. In the 17th century, Robert Boyle conducted experiments contributing to the formulation of Boyle's law, laying the groundwork for understanding the properties of gases. Boyle's law describes the relationship between the volume and pressure of a gas, stating that at constant temperature, the volume of a gas is inversely proportional to its pressure. In other words, if the volume of a gas increases, its pressure will decrease, and vice versa, as long as the temperature remains constant. This fundamental principle is crucial for understanding the behavior of gases. In the 18th century, Antoine Lavoisier conducted experiments demonstrating the conservation of mass, unraveling the secrets of chemical composition. The conservation of mass is a fundamental principle in chemistry, stating that the total mass of a closed system remains constant during any chemical reaction. In other words, the total amount of matter before a chemical reaction is equal to the total amount of matter after the reaction, provided there is no loss or gain of mass from outside the system. This principle was formulated by Antoine Lavoisier, marking a crucial milestone in the transition from alchemy to modern chemistry. The observation of the conservation of mass provides a fundamental basis for balancing chemical equations, ensuring that the total number of atoms of each element before and after a reaction remains the same, supporting the law of conservation of mass. As the list of known elements grew, scientists felt the need to organize them systematically. John Dalton proposed ideas about atomic theory, while Dmitri Mendeleev in 1869 presented the first version of the periodic table. Mendeleev, with cunning and vision, organized the elements based on their chemical properties and proposed the existence of yet-to-be-discovered elements, accurately predicting their properties. The 20th century witnessed revolutionary advances in understanding atomic structure. Niels Bohr introduced the atomic model in layers, and Schrödinger's quantum theory provided a more precise description of electron arrangement. In 1913, Niels Bohr postulated that electrons orbit the nucleus in discrete energy levels. Additionally, he proposed that the structure of an atom is determined by the number of protons in its nucleus, known as the atomic number. This atomic number is equal to the number of electrons in a neutral atom. Subsequently, in 1932, James Chadwick discovered the neutron, completing the triad of fundamental subatomic particles: protons, neutrons, and electrons. In the 1940s, Glenn T. Seaborg expanded the periodic table to include transuranic elements, further consolidating our understanding of the microscopic world. Reactions. Transuranic elements are those with atomic numbers greater than uranium, whose atomic number is 92. These elements are found after uranium in the periodic table and are typically synthesized in laboratories through nuclear reactions. Transuranic elements are known for being radioactive, and in many cases they have relatively short half-lives. Among the transuranic elements are some well-known ones, such as neptunium, Np, plutonium, Pu, americium, Am, curium, Cm, berkelium, Bk, californium, Cf, einsteinium, S, fermium, Fm, mendelevium, Md, nobelium, No, lawrencium, Linear, and beyond. The synthesis and characterization of these transuranic elements have been significant achievements in nuclear research and in understanding the properties of elements beyond uranium in the periodic table. These elements often have applications in scientific research and, in some cases, in nuclear energy-related technologies. The organization of elements is based on the structure of their atoms, which is, in turn, determined by the quantity of fundamental subatomic particles: protons, neutrons, and electrons. Information about these particles is found in the periodic table, a crucial tool in chemistry that systematically organizes and presents the elements. Each element in the periodic table is identified by its atomic number, which is equal to the number of protons in the nucleus of an atom of that element. The atomic number determines the chemical properties of the element and its position in the periodic table. Each element is represented by a unique symbol, usually 1 or 2 letters, found in the periodic table. For example, the symbol for hydrogen is H, and its atomic number is 1. The atomic mass of an element is the weighted average mass of all its isotopes, considering the relative abundance of each isotope in nature. It is expressed in atomic mass units, U. Isotopies of an element have the same number of protons, but different numbers of neutrons in the nucleus. The periodic table does not directly indicate the number of neutrons, but the atomic mass does reflect the contribution of neutrons. The periodic table organizes elements into horizontal rows called periods and vertical columns called groups. Elements in a group share similar chemical properties because they have similar electron configurations in their outermost layer. Elements in a period share a number of electron layers. In conclusion, the organization of elements is based on the number of protons, atomic number, atomic mass, and the chemical and physical properties arising from the structure of their atoms. Here are some examples of well-known elements. Hydrogen, with an atomic number of 1, is identified by the letter H on the periodic table. Its atomic mass is approximately 1.008 atomic mass units. This element has 3 main isotopes: protium, H1, deuterium, H2, and tritium, H3. It belongs to group 1 and period 1. Oxygen, with atomic number 8 and symbol O, has an atomic mass close to 16.00 atomic mass units. Among its isotopes, O16 is the most abundant, and O18 is used in isotopic tracers. In the periodic table, it is in group 16 and period 2. Nitrogen, with atomic number 7 and symbol N, has an atomic mass of approximately 14.01 atomic mass units. Its main isotopes are N14 and N15. It is classified in group 15 and period 2. Carbon, represented by the letter C, and with atomic number 6, has an atomic mass close to 12.01 atomic mass units. This element has two stable isotopes, C12 and C13, as well as a radioactive isotope, C14. On the periodic table, it is located in group 14 and period 2. Calcium, with atomic number 20 and symbol Ka, has an atomic mass of approximately 40.08 atomic mass units. Predominantly represented by the isotope K40, this element is in group 2 and period 4. Strontium, with atomic number 38 and symbol Senior, has an atomic mass of around 87.62 atomic mass units. It has several natural isotopes and is placed in group 2 and period 5. Lastly, barium, with atomic number 56 and symbol Be, has an atomic mass of approximately 137.33 atomic mass units. With the isotope Be-138 as the most common, it belongs to group 2 and period 6 in the periodic table. Today, the periodic table is a fundamental cornerstone in teaching chemistry, providing an organized representation of elements and their properties. The ongoing exploration of new elements and deeper understanding of atomic structure demonstrate that the scientific odyssey initiated by the alchemists is still alive and evolving. Each new discovery brings us closer to deciphering the fundamental mysteries of matter, leaving a legacy that inspires future generations of scientists to embark on their own quest for knowledge. And that's it for today. If you enjoyed the video, share your thoughts in the comments and give us a like. Don't forget to subscribe to the channel for more historical videos and turn on notifications. If you'd like to support the channel, you can do so through Patreon. Thank you for being here, and we'll see you on the next historical journey.